Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 12th lecture of Thermodynamics 2. Lecture 12. The contents of lecture 12 are reversed Carnot heat engine, Carnot refrigeration cycle, Carnot principle. Carnot principle includes Carnot first principle and its proof, important relationships, numerical problems, and conceptual questions and answers. Reversed Carnot heat engine or Carnot refrigeration cycle. So, as we have discussed about Carnot heat engine in the previous lecture, we know that this is the Carnot heat engine represent reversible processes. So all four processes that include in the Carnot heat engine are all reversible in nature. Therefore, when we reverse those processes, then we obtain a reversed Carnot heat engine. So the opposite of heat engine is a refrigeration cycle. So we will discuss one by one all the processes that are included in reversed Carnot heat engine or Carnot refrigeration cycle. So for process 1 to 2, this is known as adiabatic compression. So on the right hand side, top side, you can see pressure volume PV diagram, and 1 to 2 is shown here, and this is written as adiabatic compression. So 1 to 2 is an adiabatic compression process of the working fluid with the aid of external work. The temperature of the fluid rises from T2 to T1. So the low temperature is T2 to T1. So 1 to 2, and we have to provide external work for 1 to 2. For process 2 to 3, this is an isothermal compression. So you see 2 to 3, and it is written here in green color, isothermal compression. So isothermal compression of the working fluid during which heat is rejected at constant high temperature T1. So here we have temperature T1. So in the previous step from 1 to 2, it is mentioned that temperature of the fluid rises from T2 to T1. So here you see that the working fluid is rejecting heat at constant high temperature T1. So from 2 to 3, as this process is isothermal, therefore the temperature during this process will remain constant and heat will be rejected out. For process 3 to 4, this is known as adiabatic expansion. So on PV diagram, you can see process 3 to 4, and adiabatic expansion is written in on the left hand side in red color. So for process 3 to 4, adiabatic expansion of the working fluid, the temperature of the working fluid falls from T2 to T1. So the temperature during process 3 to 4, that is adiabatic expansion, the temperature will decrease. So temperature will decrease from T2 to T1. So as this is cyclic process, reverse Carnot heat engine like Carnot heat engine is also work on a cycle. So for process 4 to 1, isothermal expansion of, so on PV diagram on the bottom side you will see 4 to 1 and isothermal expansion is written in green color on the bottom side. So for process 4 to 1, isothermal expansion of air where heat is absorbed at low temperature T2 from the space being cooled. So as you can see that Q2 and arrow inside. So Q2 is absorbed during the process 4 to 1 isothermal expansion. And during, as the name suggests, isothermal, therefore the temperature to T2 will remain constant throughout the process. Now we will discuss the TS diagram that is shown on the bottom and side. So there are two processes involved, one is isothermal and one is adiabatic, then isothermal and then adiabatic. So two isothermal processes are involved and two adiabatic expansion or adiabatic process are involved. One is adiabatic expansion and one is adiabatic compression. But both are reversible adiabatic processes, therefore the value of entropy will remain constant. So for process 1 to 2 here you can see, so initial the temperature of the fluid rises from T2 to T1, therefore the temperature at point 1 is T2 and at this stage is T1. So T1 temperature and T2 temperature. So now you can compare this TS diagram with the PV diagram as well. So for process 1 to 2, that is an adiabatic compression. So for process 1 to 2, adiabatic, reversible adiabatic is also an isentropic process in which entropy will remain constant. Therefore it is written as S2 is equal to S1. So at state 1 and 2 the value of entropy is same, whereas temperature increases from T2 to T1. So you will see that there is a rise in the temperature. So the T2 is lower temperature and T1 is higher temperature. So from 1 to 2 in PV diagram and in TS diagram it's a straight line. For process 2 to 3, that is isothermal compression. So isothermal compression and heat is rejected. So for 2 to 3, that is isothermal process, therefore it is a straight line on TS diagram in parallel to x-axis. 2 to 3 is a straight line and Q1 is rejecting out. So Q1 is the amount of heat is rejected at constant high temperature T1. So T1 is higher temperature and Q1 amount of heat is rejecting to the ambient. For process 3 to 4 is adiabatic expansion. So as the name suggests, adiabatic, reversible adiabatic, like 1 to 2, 3 to 4 process is also a reversible adiabatic, that is isentropic process. Therefore the value of entropy for S3 and S4 stage will remain same. So there will be no change in the entropy, and process 3 to 4 is isentropic process. But there is a change or decrease in the temperature for 3 to 4. the temperature fall to T2. So higher temperature is T1 and the temperature is goes to T2 from T1. The temperature is decreased. Four to 1 isothermal expansion. So isothermal means that temperature will remain same and the T2 temperature T2 will remain constant and heat will be added. So Q2 amount of heat is added. So this is the complete cycle and you can compare PV and TS diagram on both sides. Note: Carnot cycle can be executed for both closed system as well as steady flow process. In Carnot cycle, all processes are reversible so that efficiency of Carnot heat engine is maximum as compared to any heat engine. Carnot cycle cannot be used in actual devices because it becomes impractical to have a reversible isothermal heat transfer process. Practical cycle with combination of adiabatic and isothermal process is Rankine cycle used in steam power plant. So we will discuss Rankine cycle when we will discuss this in lecture 15 or 16. So this topic Rankine cycle will be introduced in the later stages of your study. So you must remember that combination of adiabatic and isothermal process is used in practical cycle, that is Rankine cycle. So when we will study the Rankine cycle, you will see that Rankine cycle is a combination of adiabatic and isothermal processes. Carnot heat engine, Carnot refrigeration cycle. So the schematic diagram of Carnot heat engine and Carnot refrigeration cycle is shown on the screen, and this is a simple steam power plant that operates on Carnot cycle. So as you can see that some lines are solid lines and some are dotted arrows as well. You can see arrows in the both direction. So as you know that the Carnot heat engine is operates on a reversible cycle, therefore this process can happen in clockwise as well anti-clockwise manner. So first we will discuss if this process happen in the clockwise manner. So water enters into the pump and pump pushes the water into the boiler. Heat from high thermal energy reservoir enters into the boiler and heats the water and raises its energy and enthalpy level. So high temperature, high enthalpy, high energy steam exited out of the boiler and enter into the turbine. This steam strikes the blade of the turbine and rotates the blade of the turbine. That turbine is connected to the generator as well as a shaft that connects the turbine and pump. Let's suppose here we have a centrifugal pump, and by the rotation of that shaft the pump operates. So necessary power for the operation of pump is given out by the turbine. So that turbine is connected with the pump through that shaft, and when the steam strikes the blade of the turbine rotates and they also rotate that shaft as well. So net work is done and low enthalpy, no energy stream come out of the turbine. That is the combination of liquid, water vapor and steam. So it enters the condenser, that is a type of heat exchanger. That condenser rejects all the heat from the steam that is left out after the turbine operation and converted into liquid water, and this process continues. So that is the process of Carnot heat engine or reverse Carnot heat engine. So Carnot refrigeration cycle is the reverse of Carnot heat engine. So as you know that in refrigerator we have four components: an evaporator, a compressor, a condenser and expansion valve. So as you on the right hand side you can see dotted line, that means now that turbine is working as a pump or a compressor, so it will require work input. So we will provide dotted W arrow with, so provide with the work input. So as the working of compressor is to raise the pressure, so it will raise the pressure as well as the temperature, so it will enter into a condenser. So function of condenser is to release energy. So condenser will release energy in a high temperature reservoir. So I will draw here so you can compare both these. Here we have a compressor, condenser, that is expansion valve, and that is a evaporator. So in condenser heat is rejected out to the ambient air. So ambient air is the high temperature TH thermal energy reservoir, high temperature thermal energy reservoir, whereas the cabinet in which evaporator is installed is a low temperature thermal energy reservoir. So now you can compare both these diagram. I will start again. So that compressor is that pump, so it will increase the pressure as well as the temperature. So the condenser coil that are at the back side of your refrigerator will reject heat. So dotted line QH is rejected to the high temperature thermal energy reservoir. TH high temperature thermal energy reservoir is the ambient air. So temperature will be reduced. And now here the turbine is actually the expansion valve, so that will sudden decrease in the pressure. So for when there is a sudden decrease in the pressure, so expansion valve actually is a throttling device, so the temperature of the refrigerant will decrease significantly. So basically that will turn into the liquid in the liquid state. So then there is an evaporator, you can see here evaporator cabinet of the fridge, that is a low temperature thermal energy reservoir, and in dotted line you see that it is extracting heat from the things that are placed inside the fridge. Is the condenser or evaporator is taking away all the heat from inside the fridge, and process is a cyclic process and will continue. So you see that we have solved this schematic diagram in the clockwise manner as well as in anti-clockwise manner, because this is a reversible process. So Carnot principle. Carnot first principle: efficiency of an irreversible heat engine is always less than that of reversible one operating between the same high temperature and low temperature reservoir. So we have two Carnot principle. The first principle states that the efficiency of irreversible heat engine is less than the reversible one. If we have two thermal energy reservoir operating between same temperature, one temperature is 1000 degrees centigrade and the load thermal energy reservoir temperature is 100 degrees centigrade, and we put a reversible heat engine and irreversible heat engine between those reservoir, then the efficiency of reversible will be greater than the irreversible heat engine. So a schematic diagram of Carnot first principle is shown here. So source mean a thermal energy reservoir that is at a higher temperature, Th higher temperature, and sink mean a thermal energy reservoir that is at low temperature. So on the left hand side we have a reversible heat engine that is taking heat from high temperature thermal energy reservoir, and it is QH, and rejecting QL amount of heat in the sink. So and giving out a net amount of work done, that is WREV, that means work output of a reversible heat engine. On a right hand side you can see an irreversible heat engine is shown. So similarly irreversible heat engine is taking out QH amount of heat from high temperature thermal energy reservoir and rejecting QL amount of heat into low temperature thermal energy reservoir and giving out a net amount of work done, that is WIRR, that means work output of an irreversible heat engine. So Carnot principle suggests that WREV will be greater than WIRR. So efficiency of reversible heat engine is greater than efficiency of irreversible heat engine. Carnot second principle. The statement of Carnot second principle is efficiency of all reversible heat engines operating between two same reservoir is same regardless of working substance employed or operation details. So the second principle of Carnot explains that if we have two reversible heat engine operating between two same reservoir, then their efficiency will be same. So the schematic diagram of second principle of Carnot is shown. So on the left hand side we have a reversible heat engine 1, and on the right hand side we have a reversible heat engine 2. So reversible heat engine 1 is receiving QH1 amount of heat from high temperature thermal energy reservoir and rejecting QL1 amount of heat into low temperature thermal energy reservoir, and by doing so it is giving out WREV-1 amount of work as an output. On the right hand side Reversible heat engine 2 is receiving QH2 amount of heat from high temperature thermal energy reservoir and rejecting out QL2 amount of heat into low temperature thermal energy reservoir, and by doing so it is giving out WREV2 amount of work done. So according to second principle of Carnot states that efficiency of heat engine 1 is equal to efficiency of heat engine 2. So we can conclude that efficiency or Carnot efficiency depends upon the value of TH and TL. Therefore, it is written as efficiency is a function of TH and TL. So TH is the temperature of high temperature thermal energy reservoir, or you can say that TH is the temperature of source. So source temperature is TH, whereas TL is the temperature of low temperature thermal energy reservoir, or you can say that sink temperature is TL. So efficiency for Carnot heat engine efficiency is a function of TH and TL. Carnot principle 1 proof. So we have the proof of Carnot first principle. So the first principle suggests that if we have two heat engines, one is a reversible one and one is irreversible, then the efficiency of reversible heat engine will be greater than irreversible heat engine, provided they both have same thermal energy reservoir, both source and sink have same value of temperature. So we have to show that eta reversible or efficiency of reversible heat engine is greater than efficiency of irreversible heat engine. So let A be an irreversible heat engine and B be a reversible heat engine. So on right hand top corner you can see we have two heat engines. A is irreversible heat engine, that is on the right hand side, and B is a reversible heat engine, that is on the left hand side. Both heat engines are connected to same thermal energy reservoir, that is source TH and sink temperature is TL. So there can be three cases: either eta reversible is greater than eta irreversible, or efficiency of reversible heat engine is greater than irreversible heat engine, or efficiency of irreversible is greater than efficiency of reversible, or they have both efficiencies. So if we prove that efficiency of irreversible heat engine is greater than efficiency of reversible heat engine wrong, and if we prove that efficiency of reversible and irreversible equal wrong, then it means that efficiency of reversible is greater than efficiency of irreversible. So case 1 is, let we assume that eta A is greater than eta B. So now in case 1 we are assuming that efficiency of irreversible is greater than efficiency of reversible one. So basically we want to prove that statement wrong. Therefore efficiency formula is WA over QH. So WA over QH will be greater than WB over QH. That means as QH will be cancelled out on both hand sides and WA is greater than WB. So if efficiency of irreversible heat engine is greater than efficiency of reversible one, that is the statement we are assuming. So to prove that wrong, we are assuming this condition. So if we assume that after the assumption we have proved that efficiency of A is WA work done by heat engine A is greater than work done by heat engine B. Now, as left hand side heat engine is reversible one, so we change the direction, because that this is a reversible one, so the direction of heat engine can be changed. Therefore, it will become reverse heat engine. So it will become a refrigerator. So in heat engine, work is output, whereas in refrigerator we have to provide some work input. So it is mentioned, now let the direction is reversed for heat engine B, as B is a reversible heat engine. Now it will become Carnot refrigerator. On the previous slide, we have proved that efficiency WA is greater than WB. So, as WA is the output of heat engine A and WB is a refrigerator, and WB is the input, and WB is smaller than WA, so we will put some part of WA into heat engine or refrigerator B. So WA we put some part into as a WB, and W net is WA minus WB. That is the amount of work that can be achieved. Because WB is lesser than WA, so WB work will be input into heat engine B, and WA is the W net is the amount that is left out. As the output of heat engine B is QH, we provide this as the input QH of heat engine A. Now the function, this is a refrigerator, so it is taking out QL amount of heat from sink and rejecting QH amount into source, whereas that is a irreversible heat engine. It is taking QH amount of heat from source and rejecting QL amount of heat into sink. So we will remove the source, and as QH is the output of reversible heat engine B, we connect both these points and QH will be moved. The output of reversible heat engine B will become the input of irreversible heat engine A. But efficiency of A is greater than efficiency of B. Therefore, it violates the Kelvin-Planck statement of second law of thermodynamics. Case 2. Now we will prove that efficiency of A is not equal to efficiency of B. To prove that, we first assume that efficiency of A is equal to efficiency of B. So first we will assume and then we will prove that assumption wrong. So as both heat engine efficiencies are same, therefore their output WA will be equal to WB. So we connect the output work WA of heat engine A to input of heat engine B as work input. So as that is a reversible heat engine, we change direction, and similarly it will become a Carnot refrigerator, and it will require work, and both of these work are equal. Therefore we fed the output of heat engine A into heat engine B, and W net is equal to 0 because both are equal. Now as heat engine A is reversible Carnot heat engine, therefore it reverses Carnot refrigerator. I have already told you, as QH is the amount of heat rejected by reversible heat engine B is equal to QH taken by irreversible heat engine A. Therefore, we connect both these. As you can see that QH is the amount of heat that is rejected out by heat engine B, that is basically a refrigerator. So QH is the amount of heat that is rejected out by the refrigerator, and QH is the similar amount of heat that is taken in by heat engine A. So we remove the source and connect both these points. For heat engine A, QH is equal to WA plus QLA. For heat engine B, QH is equal to WB plus QLB. Since both these are equal, so we can equate both these equations, because on left hand side they contains QH. When we equate both these equations, then WA and WB are also equal, because we have assumed that both of these have same efficiency, which suggests that QLA and QLB are both same. So we connect both these points as well. Now this phenomena becomes, as this schematic you can see that this becomes the perpetual motion machine of third kind, PMM3. This machine, although not violates the first and second law of thermodynamics, but practically not possible due to frictional effect present. Therefore, efficiency of A is not equal to efficiency of B. Efficiency of irreversible heat engine can never be greater than efficiency of a reversible heat engine, because it will lead to the violation of Kelvin-Planck statement. Efficiency of an irreversible heat engine cannot be equal to the efficiency of reversible heat engine, because it will lead to perpetual motion machine of third kind, which is practically impossible. So both you have seen both the scenario, that when we are proving the Carnot first principle, if we believe that irreversible heat engine has greater efficiency, then it violates the Kelvin-Planck statement, and if we believe that both have same efficiency, irreversible and reversible heat engine have both efficiency, then it will lead to perpetual motion machine of third kind, and which is practically impossible. So we have proved that efficiency of irreversible heat engine is not greater than efficiency of reversible heat engine, and efficiency of irreversible heat engine is not equal to efficiency of reversible heat engine. Therefore, the only scenario left is efficiency of reversible heat engine is greater than efficiency of irreversible heat engine. So basically we have to prove that the efficiency of reversible heat engine is greater than efficiency of irreversible heat engine, and we have proved like this. So that is the proof of Carnot first principle. So here we have some important relations. So the efficiency of Carnot heat engine will always be greater than efficiency of any other heat engine. So Carnot heat engine has maximum efficiency. So you see that in actual heat engine and practically possible heat engine, Carnot heat engine efficiency is always greater than the efficiency of other heat engine or practical heat engine that are available in the market or we made in physical life. So in practical life, the efficiency of heat engine is less than the efficiency of Carnot heat engine. In ideal scenario, so it is written here, ideal heat engine, then efficiency of heat engine will be equal to Carnot heat engine. So if any heat engine has efficiency equal to efficiency of Carnot heat engine, then it is an ideal heat engine, and as it is an ideal heat engine, therefore it is practically impossible to make. However, this is also a reversible process, because Carnot heat engine is reversible process, whereas in actual heat engine the processes are irreversible. And if we calculate efficiency of any heat engine and it comes out to be greater than Carnot heat engine, then this heat engine is not possible, impossible to make. So if we are calculating the efficiency of actual heat engine, then the relation is 1 minus QL divided by QH. Whereas if we are calculating the efficiency of Carnot heat engine, then the relation is 1 minus TL over TH. If we are calculating the coefficient of performance of any refrigerator actual, so any actual refrigerator coefficient of performance, then the formula is QL divided by QH minus QL. And if we are calculating the coefficient of performance of Carnot refrigeration cycle, then the formula is TL divided by TH minus TL. And for heat pumps, if we are calculating the coefficient of performance of actual heat pump, then the formula is QH divided by QH minus QL. So for refrigerator and heat pumps, numerator is changed whereas denominator is same. And if we are calculating the coefficient performance of Carnot heat pump, then the formula is TH divided by TH minus TL. On the right hand side, also you will see that the numerator is changed for refrigerator TL and heat pump TH, whereas denominator is same for both refrigeration cycle and heat pump. So some conceptual question and answer. Suppose we forget the model of heat transfer as Q dot is equal to CA delta T. Can we draw some information about direction of Q from the second law? So the answer is, one of the classical statement of second law is the Clausius statement saying that you cannot have heat transfer from lower temperature domain to a higher temperature domain without work input. So the direction of heat transfer will be from higher temperature to lower temperature. And if we are transferring heat from low temperature to higher temperature, then we have to provide some type of work input. So the spontaneous, there are some reactions that are known as spontaneous. So spontaneously heat transfer from higher temperature to lower temperature, that means without any work input. And if we have to move heat from lower temperature to higher temperature, then we have to provide some work input. The opposite, namely a transfer of heat from higher temperature domain towards a lower temperature domain, can happen, which is a heat engine with zero efficiency. Compare two heat engines receiving the same Q, one at 1200 Kelvin and other at 1800 Kelvin. They both reject heat at 500 Kelvin. Which one is better? The maximum efficiency for the heat engine is given by Carnot heat engine efficiency, that is thermal efficiency is equal to W dot divided by Q dot H is equal to 1 minus TL over TH. Since they have the same low temperature, the one with the highest TH will have a higher efficiency and it is better. So if we have two heat engines and the sink temperature 500 is same, so the source temperature will decide the which one will have better efficiency. So the temperature 1800, a heat engine that has a source temperature of 1800 have higher efficiency and it is better. A car engine takes atmospheric air in at 20 degrees centigrade, no fuel and no exhaust. At 20 degrees centigrade producing work in the process. What do the first and second law say about it? According to the first law, energy equation is W is equal to QH minus QL, change in the energy of air. That is okay. And according to second law of thermodynamics, exchange energy with only one reservoir is not possible because this violates the Kelvin-Planck statement of second law of thermodynamics. So according to Kelvin-Planck statement, if we have to extract work from through a heat engine or work producing device, so we should have at least two thermal energy reservoir. One that is at a higher temperature is known as source, and one thermal energy reservoir that is at a lower temperature is known as sink. So until and unless we have at least two thermal energy reservoir, we cannot have the process of exchanging of energy. Does a reversible heat engine burning coal, which is practice cannot be done reversibly, have impact on our world other than depletion of coal reserve? So the answer is when we burn coal, it emits carbon dioxide during the process of combustion, which is a greenhouse gas. It absorbs and traps energy in the atmosphere that otherwise would go out into space, thus raising the overall temperature of atmosphere. Therefore, it does have an effect. During the combustion of coal, sulfur is also produced, which generates sulfuric acid, resulting in the acidic rain. So burning coal not only increase the temperature of the overall temperature of the atmosphere, but is also result in the generation of sulfur, which consequently is responsible for sulfuric acid and acidic rain. Numerical problem: a room is heated with 1500 watt electric heater. How much power can be saved if a heat pump with coefficient of performance of 2 is used instead? Assume the heat pump has to deliver 1500 watt as the Q dot H. Coefficient of performance of heat pump is Q dot H divided by W dot for QH over W. So W in is Q dot H over coefficient of performance. So power is 750 watt. So the heat pump requires an input of 750 watt, thus saving the difference. And the power saved is 1500 minus 750 is 750 watt. 750 watt power is saved. Second numerical problem: an air conditioner discards 5.1 kilowatt to the ambient with power input of 1.5 kilowatt. Find the rate of cooling and the coefficient of performance. So the schematic diagram is shown. In case of QH is equal to 5.1 kilowatt goes to the ambient, so energy equation is QL is equal to QH minus W dot 5.1 minus 1.5 is 3.6 kilowatt. So the coefficient of performance of refrigerator is given as QL divided by W. 3.6 divided by 1.5, that comes out to be 2.4. Numerical problem: a water cooler for drinking water should cool 25 liter per hour water from 18 degrees centigrade to 10 degrees centigrade using a small refrigeration unit with a coefficient of performance of 2.5. Find the rate of cooling required and the power input to the unit. So on the right hand side you can see that it's a type of heat exchanger and it is used for cooling of water. The mass flow rate is rho v dot, so it is from the continuity equation. So mass flow rate comes out to, volume flow rate is given 25 liter per hour. So to convert in mass flow rate, this volume flow rate into mass flow rate, we have comes out to be 6.93. Energy equation for heat exchanger is QL is equal to m dot H1 minus H2 is equal to m dot Cp. So enthalpy is converted into CPT, that is specific heat at constant pressure into temperature. So we have all these value and Q dot L comes out to be 0.2318 kilowatt. Formula for coefficient of performance is QL divided by W. So W dot is QL divided by beta or COP and W dot is 0.093 kilowatt. Lecture 12 Home Assignment. All students are advised to go through example problems of each topic discussed in this lecture. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. All students are advised to submit hard copies of every assignment and report. All students are advised to prepare previous lecture thoroughly before next class, as there will be a viva and oral answer question session for every student. Thank you.